So yeah. So metal was a different thing all like that. So are you waiting?
Yeah.
So okay, so perhaps I will going introduction. So it is a kind pleasure to introduce Professor Alex Lubotzky. This is in the life sometimes miracles are supposed to come very seldom, but sometimes they do come. And here is one of the miracles that we have here, Alex Lubotzky. It's an amazing thing. And I am very happy about it. Yeah, this is, I have to do more of this. Yeah, this is a big thing for us. We are very happy to have Alex Lubotzky back because Alex Lubotzky is one of the founders of Ramanujan Theatre. He's doing the great work in finite groups, in group theory, in Galois theory, in interdisciplinary work. Right now we should hear about he's talking about locally testable good codes. So his impact is enormous here. And his work was recognized with many prizes, like with Friedrich Prize, Rochdale Prize, Israel Prize, number of prizes. But the most important is that this work itself, like if you immerse in this work, it's just fantastic. He's an engaging, beautiful speaker. It's a great pleasure to have him. But before I let him allowed to speak, we have a little surprise for him. And perhaps Yossi can begin with the surprise again.
So I'm sure you guys, most of you know, we have a special guest from Israel. So we're going to sing a very famous song. Heaven Shalom Aleichem, Heaven Shalom Aleichem, Heaven Shalom Aleichem, Heaven Shalom Aleichem. Anyone knows it? Sing along. Heaven Shalom Shalom Aleichem. Welcome. It's always nice to have people from Israel. Can we do one more? Oh, say Shalom Bimromav. Oh, Yase Shalom Aleinu. Ve'al Kol Yisrael. Ve'imru, Amen. Yase Shalom, Shalom Aleinu, Ve'al Yisrael. Yase Shalom, Shalom Aleinu, Ve'al Kol Yisrael. Welcome.
Please, Alex, begin your talk. Yeah.
Thank you very much. I have to admit that I gave many lectures around the world, but I never got such an introduction. And I don't know how many of you know a little bit of Hebrew, but these songs are kind of a pray for peace, and a pray for peace. I think it's very international, and everyone that can identify itself with this. Okay. Thank you, Yossi. That was really surprised.
Thank you, Yossi, very much.
Enjoy the lecture, guys.
Say thank you. You should be in touch.
So what I like to talk today, it's sorry to start to be technical and destroy the party, is about something called a locally testable code, and I really will try to do it from scratch. The only knowledge will be more or less like second year undergraduate, not much more than that. So what is the code? What is an error-corrected code? I even don't want to assume knowledge of that. So error-corrected codes for us. Well, I guess everyone understands or heard something about the code. The point is that we want to send k bits, but this is over a noisy channel. So instead of sending k, we send n bits, n larger than k, and some of the extra bits should teach us how to correct mistakes if mistake will come up along the channel. So what we take, let's FQ be a field of order Q, usually Q equal 2. So we can really think just on Q equal 2. We just take bits like 0, 1, a sequence of K bits. Think of it. So NKD code C is a subspace of FQ to the N. So we take N bits and we take a subset of it of dimension K. What are these? These are the subset are the legitimate words. These are the correct words. We have a map from F2 to the K, with vector space of dimension K, to a vector space of dimension N. The image are the correct words, but mistakes can happen, and the receiver may receive vectors which are not in the. If you get a vector which is inside the subspace, then everything is fine. It's legitimate code. But if there are few mistakes, you get something outside, and you want to correct them, and the most likely correction is to the vector which is in the subspace, which is nearby. What is mean nearby? Nearby with respect to the Hamming matrix, like the least number of changes of bits. I mean, that's very clear. So what we want that the subspace C on one end will be K-dimensional, and better K will be as large as possible, because otherwise we are wasting a lot in there. But at the same time, we want that the vectors in the code will be in a good distance from each other, because if they are very close and there is a mistake, I will not know if to correct it to this one or to this one. So we call NKD code a subspace of dimension K, and distance at least D. What is the distance means? The distance mean is that the minimum distance between two vectors alpha and beta in the code is at least D. Now, because we assume that the subspace, that this is a linear subspace of the vector space, it's clear that the distance between alpha and beta is the same as the distance between alpha minus beta and 0. So we can define the distance as the minimum Hamming weight of alpha, where alpha is a non-zero vector in C. Hamming weight just means how many non-zero entries there are in the vector. So this is clear what we want. Up to now, we are like electrical.
This is more like L1 distance?
What?
Is this like L1 or L2 distance?
This is like L1, really,
L1, more like L1.
because we are working over so, but this is over F2, right? We take like L1 over F2.
It's not real, yeah.
Okay, up to now we are kind of electrical engineer. Where is Louis? Okay, but Louis told me on the way that she wanted something more mathematical. So more mathematical, we will treat just for you the case N going to infinity, but just for you, but already the Claude Shannon 70 years ago, who kind of initiated the theory, the mathematical theory of calculating codes, really taught us to think about the case N going to infinity. By the way, maybe some 10 or 20 years ago, this to the electrical engineer would look at the mathematician, come on, you are crazy, who cares about N going to infinity? We need N equal 128, 256. Nowadays, they're really thinking about N, which are 40,000 and even 200,000, and they are closer to infinity. Okay, so now I want to give a precise definition. A code, now, from now on, when I say code, I don't really mean one code. I mean a family of codes when N going to infinity. A code, or more precisely, a family of code is good. That's going back to Shannon, this terminology. If there exists an epsilon such that both K and D are at least epsilon times N, so that both of them grows linearly with N. it's kind of intuitively clear that K and D compete with each other. If the dimension of K is very large, we cannot keep them apart from each other. Right? There are some easy inequalities. For example, I think K plus D is at most n, or n plus 1, I think. Something like that. There are more sophisticated inequalities, but so they clearly, and the standard terminology in this area, they call the rate of the code is K over N, and the distance of the code, they usually by this, they mean the normalized distance, namely D over N. So C is good if both of them are bounded below by from 0 by some epsilon. Okay, this is clear. And the standard terminology is constant rate and constant distance. So Shannon showed that random codes, which defined by what they call random constraints, there is should be S at the end. If you take just random equations, random linear functions nulls on the vector space, take for example, if n given n takes 0.4 n equations, linear equation, and in a random way. So the set of solution is of dimension at least 0.6 n, right? That's simple linear algebra. And Shannon showed that with high probability, it will have a good, if n goes to infinity, it will have a good distance. And it's clear that it will have a good dimension because it's at least 0.6. But after Shannon, the history in the last 70 years gave many explicit examples, and usually when people want, they want also encoding method, namely what is the map from K to N, and decoding method. There is a big theory around here. I'm going to touch some aspects of it. One of the aspects which was really initiated in the 60s by Gallagher, but became very important in recent years, is it was kind of ahead of its time, is what is called LDPC code. It's a terrible name, but by the way, the computer scientists, they love initials. For me, it's I don't like it, but what can I do? I cannot change. And the codes are called LDPC, which stands for low density parity check. If C is defined by equations, which means, as I said before, linear functional, or they like to call it constraints, with bounded support. Namely, the equations that I will take are allowed to have only 17, they will touch only 17 bits. X3 plus X17 plus X125, the number of them will be only 17, independent of N. Now, Gallagher showed that if we will do something like that, still with a random equation, but all of them with a bounded support, you still get good codes. And these codes are called LDPC. They became very important theoretically as well as in practice. You can understand why this is important in practice, because if you are getting a vector of size 200,000, and you want to check whether it's a legitimate vector or not, if the equations are short, then the matrix that you have to apply in it is sparse, and it's much easier to check it quickly, right? So this is an important concept from practical as well as theoretical, And kind of another mathematical way to say that is, let's look at C perp, which is all the vectors in F to the N, which are orthogonal to alpha. For every alpha in C, what does it mean orthogonal? If you take the inner product, the scalar product, sigma AI BR, you get 0. So every vector beta like that is an equation on the code. You don't need that all of them will be short, but you need that C perp will have a basis, will have a generating set of short words. So what from C paired is the opposite of what we want from C. Right? In C, we don't want to have, we don't want it to have short words, but on the other hand, in C paired, we do want such vector. Okay, so as I said, Gallagher already showed that they exist, but explicit construction turned out to be much more difficult issue. It was open problem for like 30 years till it was solved by Sipser and Spielmann. This was the thesis of Dan Spielmann under the supervision of Sipser, and Dan Spielmann became one of the greatest computer scientists of our time. Got the Nobel Prize, and he is responsible. By the way, when he got the Nobel Prize, the committee pointed to this work as one of the three his main contribution. I'm going to show you with the full proof in three slides. It's so elementary. It's unbelievable how elementary it is. I don't think you can get the Fields Medal for something like that, but I'm not underestimating it. It's so important. It was a huge breakthrough, completely changed the area, but it's amazing how simple it is in some sense to present it. You can present it in an undergraduate course. I did. Okay, so let me do it because I think it's kind of inspiring. Let X be an R regular graph. So this is a finite graph. V is the set of vertices, E is the set of edges, and the degree of every vertex is exactly R. Now look at the adjacency matrix of X. The adjacency matrix, I guess that in this audience there are so many people who talk with me about that and know so much better than me. But still, maybe for those who don't, maybe not. Actually, it's written here. It's not written. Okay, should write it. So this is kind of if there are n point, if there are say m point in the graph, I want it to be not n but m, then this will be m by n matrix, so that if the vertices will sit here and here, and we'll write 0 or 1 if there is an edge or we don't have an edge. Now it's easy to see that if the graph is R regular, then R is an eigenvalue. You know, you take the vector R 1, 1, 1, 1, 1, 1, 1, you multiply it, you just sum up the rows and you get R. So R is an eigenvalue. It's not difficult to see the little lemma that R is the largest eigenvalue, the largest also in absolute value. So, okay, this is symmetric matrix first. So all eigenvalue is diagonalizable and all eigenvalues are real. Again, standard linear algebra. R is the largest, minus R, it always appears. Minus R is an eigenvalue if and only if the graph is bipartite. Okay. But all the others are in between. Here is a little lemma if you want to practice yourself, that the second largest eigenvalue, which is the most important for us, we'll call it lambda of X, it can be equal to R itself, but this happens only if the graph is not connected. Lambda X is less than R if and only if the graph is connected. Now we will say that X is lambda expander if for some number lambda less than R, lambda of X is less than lambda. So for a family of graphs is a family of expanders if the second largest eigenvalue is bounded away from R independent of the family. Again, we are interested in the case R is fixed, the number lambda is fixed, and all the graphs are regular and with spectral gap, with a uniform spectral gap between the second and the first eigenvalue. So assume this is what we have. The graph is called Ramanujan graph if lambda is not just less than R, but much less than R. if it is, or it should be less or equal. 2 square root of r minus 1. Where this number come from, why this is called Ramanujan, that's a long, extremely interesting story, but I will not talk about it now. I just say now two things. That's the best you can expect. You cannot do better than that. And it's not at all clear that such graph exists, but they do exist. And 30 years ago, maybe almost 40. Very difficult to admit how old I am. Sarnak and Phillips, and I on one end, and Margulis on the other end, I constructed such graph when R is a prime plus 1, and my student Morgenstern for prime powers, and then Spielman and other people did for K, not explicit, and some. There is a very a lot of work around this, but anyway, for us for today, Ramanujan graphs do exist. That's the only thing we have to know. And okay, so now let me show you what is the construction of C7 Spielman. Let X equal VE R regular. All of them lambda expand their on M vertices, R fixed, lambda fixed, and M going to infinity. M is the number of vertices going to infinity. Now they construct codes in the following way. The codes they construct are the following. First, fix and look at F2 to the R. Remember, R is fixed. That's not what we care of, right? We want to do N goes to infinity. But first of all, look at F0 to the R and fix some subspace C0 of F2 to the R. This will be called the small code. Now, label the R edges around each vertex by 1 up to R. So I have my graph, let's say R equals 3, and I will put number 1, 2, 3. And here 1, 2, 3. I don't assume any that the numbering here will be related to the number here. Just in any way you want, just fix it once forever. And then the space, the full space, the n-dimensional space will be the space of all functions on the edges of the graph to F2. So I'm putting on every edge either 0 or 1. So what's the dimension of this space? It's the number of edges, right? The number of edges is m times r divided by 2. So this is our n. What is the code? That's the secret. The code is going to be this. Is going to be all functions on the edges, such that for every vertex V of the graph, the local view of V on the link is in C0. Think about a single vertex, and you have a function on the edges. You look at a single vertex, the vertex around it sees 1, 1, 0, 1, whatever. So it sees a vector in F2 to the R. Because the degree is up, right? And we put labels so we know exactly what it means. We require that all those vectors will be inside the small code C0. Okay, that's the way we do. Now the claim is, and that's really the theorem of Simpson-Spielman, if the dimension of the small code is more than R over 2, and the distance of the small code is more than lambda of X. Now this is an interesting condition, because the distance of C0 is about the vector space. The lambda of X is about the graph, right? There are two things are not related at all. Both of them are between 0 to R. Right, lambda x, you remember, it's less than r, but and the distance is also at most r because we are inside an r-dimensional space. So we need lambda x to be very small. So like Ramanujan, 2 square root r minus 1, fairly much smaller. You know, r maybe it should not be too small, but then C is an LDPC good code. Okay, let me give you almost the full proof. Why this is LDPC? Usually LDPC is the difficult part. This is trivial. Every condition is a local condition, right? When a vector is in the graph, if the vector, if for every vertex, the vector that you see around it is inside C0. This can be written as equations whose support is at most R. Right? And only look at R vector. So that's trivial. Now, what is the dimension of this space? It's embarrassingly trivial, because the dimension of C is n, the total number, minus it's at least minus the number of equations. The number of equations is for every vertex, there are m vertices. You write the equations defining C0. There are, right? The codimension of C0 in R is R minus theta. Okay, I think you believe me for this computation. If not, if somebody record it, you can check. And then what I'm getting, some constant 2 over R, the dimension of C0 minus R over 2. You see why we need it to be positive, right? Times n. So this is good in the sense of dimension. The proof that it's also good in the sense of distance is slightly more difficult, but not much more. What we need, what we need to show here? We need to show that every vector in the code has large support, linear in the size of the graph. What is a vector in the code? It's a function, non-zero, which satisfies all these local conditions, right? Okay, let's F be such a function, and let capital F be the support of it, namely the set of edges for which little f is not zero. And let G be the subgraph of X spanned by F. Now, here is a simple lemma of Alon and Chang. I will not prove it to you, but believe me, the proof is half a page. And if you will give me another 10 minutes, I would do it. It's not a big, you can do it in undergraduate course, and people know a little bit of inner product and something like that. So I said second year, maybe not first year, but advanced first year. If you have a subgraph of a graph such that the average degree of it is more than the second largest eigenvalue, then the size of the subgraph is linear in the size of the graph, is 1 over R, this average minus lambda x. So if it's bigger than that, this is constant. That's exactly what we need. Now, why this happens in our case, just now think about it. In our case, we look at the function, we look at the vertex in which is inside the subgraph. What is the degree of the subgraph? You remember, what is the graph, the subgraph G? It's the one spanned by F. F is the support of little. If the function F is not zero here, which means that at least one of edges here is not zero. But you remember the condition, the distance of C0 should be bigger than lambda x. What does it mean? It exactly means that if one is not zero, then it has few more here which are not zero more than lambda x. Right? So not only that the average degree is more than lambda x, in every single vertex of the graph, the degree is more than lambda x. And we finished. This is the end of the proof. So, okay, to give the proof, you need to know that there is this graph and there is this code C0 satisfying this property. And okay, take my word for that. But it exists. By the way, you don't really need even Ramanujan graphs. I mean, I just wanted to to sell you my work. You need, I actually complain about Simpson and Spielman that they call their paper expander graph. They use our graph, but there's something a little bit misleading because expander just means that the second largest eigenvalue is slightly less than R. Here you really need it to be substantially less. You don't have to be optimal, but it should be much less than R. Okay, so this is the LDPC. But only now I'm starting my real talk. Why? Because Spinner in the introduction to his thesis, in fact, said that he wanted to solve another problem. What he wanted to solve is not low density, not LDPC, but LTC. What is LTC? Locally testable code. So that's what I want to, that is my talk about locally testable code. By the way, it's known that every locally testable code is also low LDPC code. But local testable require more. And it's not so clear that it's more, but it is more. Okay, so now let's be careful and give the definition. Some of you are familiar with what is called PCP theorem in computer science. Provable, checkable proof may see the connection, but I don't have time to elaborate. Luckily, because I don't understand it. Okay, so a code in F2 to the N is called Q epsilon, locally testable code. If there exists a random algorithm A, such that for every alpha in F2 to the N, A read only Q random bits of alpha. So we are looking for an algorithm, a random algorithm, which get a huge vector of size n is 200,000 or million or whatever, reads only 30 bits out of it, read only 30 random bits out of it, it does not read, and should answer if the vector is inside the code or not. This is of course rubbish because that's impossible. But what we want, that it will answer with high probability if it is close to the code or far from the code. Why? This is extremely important theoretically, but even practically. Let me explain. You send in these days, as I said, you said a vector of length 200,000. You have a code which you use or something, but the code can correct if the number of mistakes is 5%. If it's 40%, it's crap. I mean, you don't want to read all the 200,000 bits to apply all your correction and then discover that you got rubbish, right? And then send me again. You want to read very few and very quickly to understand if it's at least close. If it's close, then you will apply So this was a problem of a huge theoretical, but nowadays also practical important, that you need a random algorithm that will answer yes if you are really in the code, and will answer no if you are far away. If A is more than epsilon, the distance to the code, the normalized distance, right? The probability is between 0 to 1. So you say if the normalized distance, the distance divided by 1 over n is large, then you want these two to say no. By the way, if you think about it for a second, you see that you can really, by doing it several times, but a bounded number of times, independent of n, you can get as good probability and as far as you really need. Okay. So the issue here that you have to decide on a long vector by reading only bounded amount of bits. Is it possible or not? Well, over the years, experts dispute about the issue. There was a large group of people who believe that this is impossible, and they even try to prove lower bound. Now, when I say impossible, sorry, this is certainly possible. But let me explain. Here is we started much later, especially in the
You have enough time.
Okay, so I have enough time. I want, because I want to show you this. I mean, it's elementary, but it's extremely important. I mean, what maybe even started on this subject was the following. Let W, I'll give you an example of a code which is locally tested. Let W be, you look at the vector space F2 to the M, and you look at all functions from it to F2. And then, so what is the dimension of this code? It's all functions on a set of size 2 to the M. That's exponential in M. So N is 2 to the M. What is the code? The code is only the linear functions. Okay, and so the dimension of the code is M, which is log of M. So this is not a good code, right? Then, by the way, the distance of it is fantastic. It's a nice exercise, but the rate of it is terrible. It's only logarithmic, but it's locally testable. What will be the test? Very simple. Choose random two random vectors in F2 to the N, and the code will read only 3 bits: f of x plus y, f of x, and f of y. If they satisfy it, you will say yes. If they don't satisfy, you will say no. A theorem which nowadays they of Bloom, Luby, and Rubinfeld, but they all computer scientists always call it the VLR theorem. I told you that the probability that it answer no is at least 2/27. This is the epsilon of the distance of f from being linear. So this is a 2/27 LTC code, but it's far from being good. There are actually more LTC codes. There is the famous Reed-Solomon code in LTC, but not good for a different reason, for distances. There is the Reed-Muller also problem with the distance. By the way, these are very huge in practice, Reed and Muller, but they are used in small n for specific n, so they don't care so much. I want to say a few words about the tensor code because we are going to use it later. The tensor code is the following type of code. Let's take N1 and N2. Actually, let's take N1 and N2 be equal to each other. Let's C1 be inside F2 to the N1, a smooth code. I will skip the definition. Almost every code is smooth. And C2, it's also, you can even take C2 to be equal to C1, that's no problem. And think about N1 and N2 as equal to each other, that's the best. Look at the tensor product of these two subspaces inside the tensor product of 2D2 space. Tensor product, it's not a fancy thing. The tensor product is just the N1, okay, N1 and N2 are equal. It's just the N by N matrices. And the code will be simply the matrices such that all the rows are in the small code, and all the columns are in the small code. Okay, so this is a code whose dimension is whose length is n squared. The dimension you can see is linear in n squared. That's no problem. The distance is also okay. It's locally testable in a weak sense. What is the test here? Pick up a random row or pick a random column and check if it is inside the code. But if you pick a random row, you read n bits out of n squared. So it's, but I allow you to read only a constant number. of bits, right? So it's locally testable in a weak sense. But over the years, when people, for 30, 40 years, they look for some code, they try to make compromises. Okay, we cannot get it. Maybe we can get the distance a little bit less and Q equal problem. But the real question was always, that's the long-standing problem. Are there good LTC code? Can you get all of them, all the good properties, namely constant number of queries and the constant rate and constant distance? The nickname of this problem was the CQ problem. Why? Constant rate, constant distance, and constant number of queries. Okay, why this problem was so difficult? This is important to explain. Because I told you that Shannon work was, first of all, random are good. Gallagher work said LDPC random are good. Now every LTC must be every local tested good must be LDPC. Okay, so let's look at random LDPC. They are not LTC. Random codes are not locally testable. So even if you know that random are whatever property you want, to find an explicit construction is a very difficult problem. As I told you, it took 30 years between Gallagher and Sipler and Spielman, between the 60s and the 90s, to find an explicit construction. But here, the random are not. So the question, are there LTC at all? So like they say the following, to find an explicit construction among random is like find an haystack in a pile of haystack. To find LTC is like finding a needle in an haystack, and it's not even clear that the needle exists. And in fact, there was a dispute in the community among experts whether some group people conjecture that they exist, some other conjecture that they do not exist. Interestingly enough, there was an intersection between a famous computer scientist who is even a friend of mine, a colleague of mine, ordered the Goldreich, changed his mind over the years. In the first book, he wrote something like that. In the second book, he conjectured that but he admitted that he convinced that. Okay, so the good news of today is that they do exist, and this is joint work with Irit Dinur, Shai Evrar, Ron Livne, and Shachar Moses. We constructed explicit construction of locally testable good code. So the with constant W. It's kind of amazing that this problem was open for like 30 years. And suddenly, at the same week, 2 papers were put on the archive solving the problem. We put, as well as Panteliv and Culture from Moscow, independently provided the construction also of LTC. They came from a completely different direction. They wanted to solve another problem. The problem they wanted to solve, it was they are people of quantum error-correcting codes. And there was, for a good number of years, the problem, can you find good LDPC quantum codes? Like what Sipler Spielman did classically, they tried to do for quantum, there were some partial results, etc., etc. Even I was little involved in some of the small steps, but they went so much further. What I completely was not aware of, that except that that you can use it. And I mean, okay, it's because of the construction they made. They noticed that along the way we can get also LTC. What is interesting, and I have to admit that that's fairly new, and I didn't have a chance to read it truly. You know, in my old age, difficult for me to learn these things. The method to solve it is to assign a student to learn. So I assign a student to learn, but it takes him a while. Actually, just today I got an email from him. Oh, I want to meet you. I have something to say. So I hope I know better. So which work I want to really to learn is a work of Sam or Short that if you start with our LTC, you can go backwards and also solve the quantum problem. The sum, just like they solve the quantum problem and deduce LTC classical, one can go from not from general LTC classical, from our LTC and get solution also to the quantum. So the two problems are okay. So now the last thing I want to do, basically, and maybe if I have time, I'll tell you where all this come from. I want to present our course. You want to ask something? No. Okay. So here is our construction. And you see it's very much influenced by the Sitter-Spielmann. In fact, I'd say it right away, we do a second floor to split a Sitter-Spielmann first floor. Sitter-Spielmann work with graphs. We work with a two-dimensional square complex instead of graphs. Okay, so let me show you how to get this two-dimensional. Let G be a finite group with two symmetric sets of generators. So if you have a group and a set of generators, so it's fairly the construction of Cayley graph. You have a group G, you have a set of generator S is a subset of G. Then I hope we all know, or if you don't know, here's the definition, the Cayley graph of G with respect to S. This is a graph that the points are the elements of G and G, and you multiply every, so this is GS1, this is GS2, so GS3, you multiply by the elements of S, right? The neighbors are multiplied by the elements of S. Now, people are doing a Cayley graph for more than 100 years by now. And okay, I multiply from the right. I could multiply from the left. And usually when people say Cayley graph, they even don't bother to tell you if they do it from the right or to the left. Why? Because a little exercise that the Cayley graph, the left Cayley graph is isomorphic to the right Cayley graph. They're not equal, but they're isomorphic. So people don't care. Somehow, for a reason which retrospectively I don't understand, I never saw any work which do both. And we do both. We for convenience, we are making the following assumption. They're not crucial, but some of them are convenient. First of all, we take two sets of generators A and B. None of them contains identity, and we also assume that in a way they are very much independent of each other. Namely, no element of A is conjugate to any element of B. Right, so for every A in A, B in B, and G in G, G to the minus 1 AG is not B. Okay, now but let's assume that they're of the same size. It's again not crucial, just convenient. And let's assume that both of them, both Cayley graph, are Ramanujan graph, namely that the second largest eigenvalue is less or equal to square root of R minus 1. Again, this is not crucial, but it's crucial that it will be much, much less than R. But we know to do it, we have, why not? You know, it's always a pleasure to use some work you did when you were young, right? So we have example like that. That's not an issue. Now we define what we call left-right Cayley complex, that we act from both sides. But we act from both sides, and we want to think of it as a two-dimensional object, not as a one-dimensional object. So we act with, if you take an element G, you multiply it by A from the left to get AG, you multiply it by B to get GB, and then you multiply A here to get AGB, and then if you multiply by B from here, you get AGB. And we think of this as a square. So we think of this object not just as a one-dimensional object, but as a two-dimensional object. We have vertices, we have edges, both like from the right or from the left, and we have these triangles. So I mean, the condition of the T and C that they wrote, just make sure that all the four vertices are different. It's not so crucial. Anyway, if you count, you see that the number of a square is 1 over the size of G, A, B, etc., etc. Okay, now again, we take the size of A and the size of B, R, and R is fixed, you remember, R fixed, and the size of G going to infinity. Now we take C inside F to the A to be a smooth chord, and CB and C to the B. Well, we can take the same chord because both of them are of order R, and we take this tensor chord that we mentioned before, right? It's like a show of breath, right? If a pistol is on the table in the first stage, it will shoot later on. So this is going to shoot now. But before saying that, let's think about it for a second. What are the squares touching a given little g? Right? For every given little g, I can go A and B, and I can do that. So the number of squares touching little g is exactly R squared. And in fact, I can really identify them with the names. I can identify them with the set A cross P. So there is one-to-one correspondence between the squares touching any given vertex G and A cross B. Okay. Now, what is the code? The code will be a kind of a Sitter-Spillman code, but on a second floor, not on the first floor. We will take all functions on squares to F2 on the squares. Now, look at such a function and localize it to a vertex. What a vertex is, it sees around itself A cross P. So you get a matrix. We want is that what you see is what this little vertex sees will be in this tensor code. Okay, this is our code, and you can say it in a different language, because if you remember, the tensor code means that for every edge, the link of the edge is in one, and the other links is the same. Now, the theorem is a little bit more ugly than the theorem of Sitter-Spillman, but not much. But I save you there because that's not so interesting. The theorem now says that if you make these choices of the code to be good enough in regarding distance and regarding distance and rate, then the local code is in some sense LTC. It's a fixed size. But you remember I told you that the tensor code is LTC. Just it's LTC with if you think of it going to infinity, it reads a lot of bits. But if you fix R, then you read only a bundle number of bits, right? So it's a kind of the local code is local testable. You see? And we are using that property, or maybe let me say it in another way. If you follow my proof for the Sitter-Spillman, we propagate the dimension of the little code to the big code. Then we use, this was almost trivial, right? By the equation. We propagated using the Alon-Chan lemma, the distance of the local code to a distance of the big code. Here, the proof is much more complicated, but we propagate the local testability, of the tensor code to a local testability of the good code. But it needs much more work. This is a colloquium. I will save you that. So that's, but in principle, that's also elementary. I mean, there is nothing here which you cannot present, but it will take a few hours. Instead of that, I want to do something more interesting. And this is kind of introduction. If you come again, I will talk about it. Because I want, so in a way, as you can see, we are doing something which is inspired by Sitter-Spillman. Why it took so many years to do? I think that really what was important in our approach was the belief that the right way is to go to the second floor. And I want to explain where this comes from. And I'm afraid now that if up to now the talk was very elementary, it's not, the explanation is not elementary. But the proof is elementary. But some of the motivation to get it. So for the inspiration for these codes and on the left Cayley complex came from what is called I-dimensional expander. I-dimensional expander is a theory which is built over the last, it became very popular in the last 5 years, but it's already at least 10 years, 15 years, and if you want, you can even think about it 40 years, it's a different language. I'll say something in a moment. Which is, you want to take the notion of expanders, which are for graph, and to define it for hypergraph for simplicial complexes. What does it mean? The honest answer is we don't know. Because there are many definitions. And what is the beauty of expander? That there is a combinatorial definition. Over lunch, I explained some of the people here, which is equivalent to the spectral definition. There are several other definitions. Each one of these definitions, you can think about several ways how to generalize it to I-dimensional. So you get a lot of possible, and they're not anymore equivalent. Sometimes they are, sometimes they're not. And part of the work is to understand if they're equivalent, if one implies the other, etc. But there are various things and the definition. Really, what should be taught as the earliest work on I-dimensional expander is the work of Garland already in 1972. I want to say a few words about that, and I apologize in advance that here I'm going to use some fancy words, which I will be happy to explain them, but I need more than 10 minutes or 5 minutes, whatever time left for me. So let G be a p-adic simple Lie group. So p-adic numbers is a kind of an analog to the real numbers, which is a fantastic world that only mathematicians love, but Jan and I, we are lovers of this world. And you can talk about, just like you talk about Lie group over the real number, you can talk about Lie groups over the p-adic number. For example, SLN QP. QP is the p-adic number. It's a Lie group, it's an infinite locally compact. Let gamma be a co-compact lattice in G, which means a discrete subgroup in G, so the G mod gamma is compact. Now, in 1972, Garland proved a conjecture of Serre, which says the following: for every I greater or equal 1 and strictly less than the rank of G. The rank is some invariant that you can associate with every such algebraic group. For example, the rank of SLN is n-1. Anyway, for every such number between 1 and the rank, the I cohomology of gamma with coefficients in V is 0 for every, well, here I'm cheating a bit. Garland proved it just for finite dimensional unit representation. Later, people extend it to infinite dimensional. But what is it? But now, more than the results, is important for us is method of proof. Its method of proof was from local to global in the following sense. If you take a real Lie group like SL2R, it acts on the upper half plane, the two-dimensional hyperbolic plane. Take a general simple Lie group, it acts on some symmetric space, which is a Riemannian. Over the p-adics, Boer and Titz constructed the analog of the symmetric spaces. These, they are called Boer-Titz building associated with G. Now, these are constructible simplicial complexes whose dimension is equal to the rank of G. For example, in the simplest case, another tip for you, sorry. For SL2QP, the rank of SLN is n-1. For SL2, 2 minus 1 is 1, so it's a one-dimensional contractible simplicial complex is actually just a P+1 regular tree, and G acts on it from what? So you can associate the building. Then when you let a lattice act on B, you get a finite simplicial complex. If you do it in SL2, you get a finite graph. In fact, the Ramanujan graph that I told you about before were constructed by us using this what it's tree and a lot of arithmetic information. So the name Ramanujan is not accidental in this story. Okay, Garland, but now we are talking Garland deduced that so what did Garland wanted to prove the vanishing of that cohomology. That cohomology can, and one of the interpretation of this cohomology is using I-dimensional Laplacian of the simplicial complexes. What Garland did, he showed that if you know, and he proved spectral gap for them, and spectral gap for them imply vanishing of the cohomology. For those who are really know the theory, it's trivial. For those who don't know the theory, it's not complicated. That's something I could explain in, but I need half an hour. But his ingenious idea was that he used the fact that the link of every such simplicial complex is an excellent, that's something which is well understood. It's a simplicial complex of legs over finite fields. They are well understood, not difficult to compute the spectral gap of them. And he showed that the local spectral gap of them implies the global spectral gap of the higher dimensional Laplacian. Now, if you think about it for a second, then first I want to say two remarks. First of all, this is something which cannot happen in dimension one. Because dimension one, the link of a vector is just a set. There is nothing there that you can do. And indeed, it's not difficult to give examples of two families of graph, which was locally exactly the same. One of them is expander, and the other is very far from being expanded. Namely, the local structure does not affect the global expansion. What Garland did is to show that in dimension 2 and I, the local has a dramatic influence about the global. I have to confess, I know this theorem of Garland for probably 30 years. Only 5 years ago, when I started to be interested in this I-dimensional expander and I learned about this code, I suddenly understood that it must be that Garland is really locally testable. What is locally testable? Locally testable means that if you know something locally, you can deduce global information for that. So I almost religiously believe that this is the right tool. And then I started to work with these people, and we work and we try to do something very fancy, periodic uniformization, some work of reconnection with algebraic surfaces. I mean, you won't believe how far we went. I even forced a young colleague of mine to give a full course on that because I wanted to learn, because I had the feeling that it will help this periodic uniform. Luckily, we had in our group, Irid Dinur, who is a down-to-earth computer science. And when we did to that, Odessa said, why are you doing all this? After we suffer for students, why don't we try just to do two Ramanujan graph and combine them from both sides? And suddenly, everything went, and that's what we brought. But somehow, I stress this, I'm really stressing this because I want to say that what Garland proved what Garland proved in a way is exactly such a local to global. This cannot work for graph. Okay, I say all of this thing they said without this. So the real idea we wanted to do read Solomon code. So we had the same type of idea. Take a code which is little bit locally testable, not good when you go to the infinity. Put it on the links and then deduce something for the middle. So eventually, what we came was just taking something much simpler than all this. I still am a little bit sorry that I mean, I believe that maybe some smarter people will still be able to make this. So if you want to do a complicated work instead of a simple work, that's your opportunity. Okay, thank you very much.
Well, so thank you very much. Great talk. So any questions? Yeah, please. Yeah.
So is this Garland theorem true over R? Means vanishing homology?
No, absolutely no. That's that's very, very. In fact, I recently wrote a paper with the father and the Weinberger. There is this vanishing of cohomology is important also for other reasons called stability. Which I don't know, it's only related somehow, but the theorem of the Garland as it is nothing. But somehow we have a kind of replacement for that. I'll give you an easy example to see that it's not true. H1 did vanish in Iran, that's Kashaf over the. But take a group like the symplectic group, take sp2gr. This has a universal carbon with a one-dimensional group, which means that H2 of this group with coefficients in R are not trivial. But nowadays, we know that in some sense, this is the only counterexample. Wow. So you can kind of run away from it, and for the application of stability, it still works. And stability is locally testable in some sense. But that's I will maybe explain another time. Yeah, this I give the sequence of this. It's all related somehow.
You have to come and deliver the sequence. Yeah. So any other questions?
Maybe I ask, what says motivation for this conjecture?
Well, Senner is in Borel, you know, these people will always be interested.
What in his intuition, I would say. What was his intuition?
To be honest, I don't know. I know Senner many few times, but I never asked him about that one. You still active, he's 95. But yeah, I someone got a little chance to. I mean, I guess maybe made some computation, maybe you already at that time, for example, the DT, so he saw that rank is bigger than one, H1 band is. But I don't know. It's I really have to think about it. I mean, I have to think. I mean, sell is sell.
Yeah, also like you were making squares, so and you have this higher dimensional thing. So do you think about cubes?
Okay, so that's yes. I mean, I think about cubes with high dimensional expander.
Yes.
But I wonder, here's a very, very simple problem. Is it possible to generalize K-graph to cube?
Yes.
Because group has two sides. You don't have another side.
Yeah, I'm thinking about it.
So I think that because almost every time I gave this talk, I was asked this, and then I think that one time I convinced myself that we are using the fact that the two actions commute with each other, and if you have a group with three actions on itself, which every two commute, I think it must be a billion. And if you're billion, it's not expanded. So at least I don't see how to do this type of thing right away. But the Garland work is in any dimension, and they are fascinating. We constructed explicit Ramanujan complexes, and that's what the talk I gave in Toronto.
Yes. In what kind of groups and generators in AB you prefer? Like.
No, I don't. I mean, for this case, you know, in the what is called now is LPS. Very explicit. Take that. If you prefer my student Morgenstern, you can take them. If you prefer, doesn't matter really which one. It's not doesn't play a role. Only the fact that they are. And to be honest, as I said, you don't really need Ramanujan if you have another way to get something which is, but it should be very much smaller than R. I see. If it will be, you know, I don't know, square root of R, but not like 7 square root of R, it doesn't matter.
Any other questions, anybody? Okay, then thank you very much. It was all Alex, what those, right to.
The cooler and salt. But this big of reach. Yeah. I think you should be putting out parents and cheap. Some. I told them we need there.
I was afraid they would take all this away.
No, I learned it, but
Because their accent.
really,
They something.
apart from the French lessons, though, I only know that